Hello everyone. So today I have quite an interesting question for you, and we're gonna learn Vieta relations, AM-GM, and playing with graphs. Now I know that these are topics that we have got before, but this is slightly different kind of a problem, and the kind of the takeaway is gonna be the graphical interpretation of this problem. How are we gonna see how we're gonna essentially see how a cubic is dealt with graphically. So I hope you have fun, and let's begin. This is a problem number 24 from the AMC 12A in 2016. And in this video, we're going to learn about Vieta's relations, the AM-GM inequality, of course, the graphical interpretation of this problem. And I'm also going to talk a little bit about the Descartes rule of sign change. The Descartes rule of sign change, I'll elaborate on that more later. And after that, we have certain book sessions for the AMC and a very similar but challenging problem. So let's begin.
This video is sponsored by Cheenta.com. Since 2010, Cheenta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI-CMI entrances, and research projects for school and college students.
Okay, so what have they given us? They've given us is there's a smallest possible real number A such that there exists a positive real number B, so that all the roots of the given polynomial, the given cubic polynomial, are real. Okay. In fact, for this value of A, the value of B is unique. What is the value of B? Now, okay, if there's something called as Descartes rule of sign change. Okay. Descartes rule of sign change. So what it essentially states that the maximum number of positive roots is equal to the number of sign changes in the polynomial. The maximum number of positive roots is the number of sign changes in the polynomial, right, in P of x. Let me just state it that way. Okay, so here if I define P of x to be equal to x cubed minus ax squared plus bx minus a, how many sign changes are there? So if you see, this is positive 1 over here, right? Positives to negatives, that's one sign change. Negative to positive is another sign change, and positive to negative, another sign change. So in total, we have 3 sign changes over here. Therefore, it's a cubic, and cubic has 3 roots. And we have seen by Descartes' rule of sign change that all 3 roots are positive. Okay, there were 3 roots. There were 3 positive roots. Maximum number of positive roots is 3, and therefore all 3 roots are positive from Descartes' rule of sign change. Now that's really good, because now I can apply something called as the AM-GM inequality. So let the roots be alpha, beta, gamma. Alpha, beta, gamma. And by Vieta's relations, we essentially know that alpha plus beta plus gamma is minus b by a. That will be a. And alpha, beta, gamma will be nothing but minus d by a, which is also a. Right? Now, essentially, we can know that alpha plus beta plus gamma divided by 3 is greater than or equal to the cube root of alpha, beta, gamma from the AM-GM inequality, of course. And so a by 3 is greater than or equal to cube root of a. And if I just cube on both sides, I'll get a cubed by 27 is greater than or equal to a. So a squared is greater than or equal to 27, and a is greater than or equal to 3 root 3. But they have asked for the smallest possible value of a, therefore a minimum is 3 root 3, which is what we had in the question. Now, because we have found a, right, now we can find other quantities. Now, here obviously we saw that alpha is equal to beta is equal to gamma, right? Now, if alpha is equal to beta is equal to gamma, and alpha plus beta plus gamma it was a, I can essentially write that 3 alpha is equal to a, so alpha is equal to a by 3, right? So alpha is essentially root 3. So I got the 3 roots. Alpha is equal to beta is equal to gamma is equal to root 3, right? And okay, now again from Vieta's relations, I can state that what is b, right? What is b? B, I believe, the coefficient of the the linear term, right? So b is nothing but alpha beta is beta gamma plus gamma alpha. That is nothing but root 3 times root 3, which is root 3 squared plus root 3 squared plus root 3 squared. So beta is 3 plus 3 plus 3, which is 9. So we found the value of b that was which we had to find in the question, and yeah, that was where we stopped. Now obviously AMC is a time bound exam. You're free to move forward to question number 25 or any other problem that you haven't solved. But now what we're going to do is we're going to look at the graphical interpretation of this problem. Essentially, we're going to look at how does this, maybe look on a graph. Let's play around with graphs a little bit over here. Okay, so from Descartes' rule of sign change, we have essentially figured out that it has 3 roots, obviously, and it has all 3 roots are positive, right? So let's consider case 1. We have 3 distinct roots. Okay, 3 distinct roots of the cubic. So let me just draw a rough graph. It looks something like this, right? This is the first root, this is the second root, and this is the third root of the polynomial p of x. Now let me just write it down again. So p of x, what it was I believe x cubed minus ax squared plus bx minus a, right? Yeah, it was that. So now, well, what can we do over here? Now, well, they're also given us that a is unique, so b is unique, right? For that smallest value of a, b is unique. That's actually very, very important, because if you see in this graph, b is not unique. Why is it not unique? Because if I essentially increase b by a very small amount, for example, if I just increase b by delta b, what will happen to this polynomial? It will shift a little bit towards the left, right? So if it shifts towards the left, it's essentially going to have 3 roots again, right? So let me just trace down the new polynomial. It's going to look something like this. But effectively, it again has 3 real roots, right? So therefore, b is not unique, right? So this case essentially fails, right? Then we have case 2. It has 2 distinct roots. Now, if it has 2 distinct roots, one is the repeated root, right? So here we essentially have like 2 possibilities. One is that if it looks something like this, now let's consider that this is the repeated root and this is the other distinct root. Now, if this is the value of a polynomial p of x, then again, you're using kind of the same thought process. If we increase b by a very small amount, very small amount, what will happen to this? It'll shift a little bit over here, right? And this will actually shift a little bit up. This will actually shift a little bit up. So this gives us 2 roots over here and the third root over here, right? Let's use another pen if you want. So it gives us 2 roots over here and the third root over here, right? So it again gives us like 3 roots, right? So again, it means that b is not unique, and therefore this case also fails. So we are just taking out the uniqueness of b using the graphs. So this gives 3 real roots. Again, b cannot be unique, and therefore this case is also wrong. It's specifically given to us in the question that for this value of a, b is unique. And I think that's a very important part. For this value of a, b is unique. Smallest possible real number a. These 2 were kind of like really important over here. And yeah, in the first case, we again saw that if you increase b by a very small amount, the graph just a little bit towards the left, and we again have three roots. Case 1 and case 2 both fail. So that essentially, or okay, we can actually draw another graph. So for case 2 in case 2 itself, there is another possibility. What is the other possibility? So other possibility is the graphs looks something like this. It will look like this. So yeah, again, this is essentially the repeated root. Now again, like using completely the same ideology, this time I will decrease b by some amount, let's say delta b. What will happen? This thing will just shift a little bit towards the here. This thing will go a little bit downwards. So again, we're going to have 2 roots, and this is the third root, right? So again, we're essentially going to have 3 roots, and again we see that b is not unique, right? We essentially sketched out the 3 roots over here if we just subtract b with some small value delta b. So again, b is not unique over here, so therefore this case also fails. So the only case that remains is case 3. All roots are equal, which is what we figured out using the first method itself. So all roots are equal. So essentially, the given polynomial p of x is equal to x cubed minus ax squared plus bx minus a has to be of the form x minus r whole cubed for some particular value of r. And essentially after that, what you would do is there are a few ways to go about this. Obviously you can all 3 roots are equal, so let them be alpha alpha alpha. 3 alpha is a, so therefore alpha is equal to a by 3. So therefore this is of the form x minus a by 3 whole cube. Again, product of the roots is a by 3 times a by 3 times a by 3 is nothing but a. Since a is non-zero, you can cancel it. So a square is equal to 27. A is equal to 3 root 3. And b is nothing but 3 times alpha squared, I believe. Right? Because alpha. So it is 3 times alpha squared. Alpha was a by 3. So this would be a squared by 9. So there would be a squared by 3. A squared is 27 by 3, which is 9. So yeah, essentially that is what you would get using the graphical interpretation as well. I think those things were the takeaways from this problem. Obviously, you can use Vietas, and that's a quicker method, probably a better method as well. But I think the graphical interpretation was really good to know in this problem. Okay, coming on to certain book suggestions for the AMC. We have Mathematics Can Be Fun by Yakov Perelman, Mathematical Circle in the Russian Experience, Algebra Can Be Fun by Yakov Perelman, Excursion Mathematics, Challenges and Theories of Pre-College Mathematics, and Elementary Number Theory by David Burton. Now after that, we have a relatively similar but challenging problem. This is again involving Vieta's relations. Okay, so they've given us the quadratic polynomial with real coefficients and leading coefficients 1. That's a monic polynomial. It's called disrespectful if the equation p of x equal to 0 is satisfied by exactly 3 real numbers. Okay, among all the disrespectful quadratic polynomials, there is a unique such polynomial p of x for which the sum of roots is maximized. Okay, find p of 1. So this is a very interesting problem, and if you're able to make some progress on it, or if you're able to solve it, please let me know in the comment section below. And until then, I'll see you in the next video. Thank you very much. Bye-bye.
The programs are designed for students who are passionate about mathematics, and they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Cheenta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Cheenta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit cheenta.com.